Welcome to this walkthrough of problem number 280, Wiggle Sort. In this session, we'll explore an interesting array manipulation problem, break it down step by step, and discuss various approaches to solve it effectively. Let's dive in. In this problem, we're given an integer array called nums, and our goal is to reorder it to satisfy a specific pattern known as the wiggle property. This means that the elements should alternate between being less than or equal to their neighbors and greater than or equal to their neighbors. For example, nums 0 should be less than or equal to nums 1, then nums 1 should be greater than or equal to nums 2, and so on. Importantly, we need to modify the array directly, or in place, without using extra memory for another array. The problem requires us to ensure this wiggle condition is satisfied for the entire array. The input will be an integer array nums of length n, and the output should be the same array, but reordered to achieve this wiggle property. Let's look at some examples to see this in action. In the first example, we're given the input array 3, 5, 2, 1, 6, 4. After reordering, one possible valid output is 3, 5, 1, 6, 2, 4. Let's break this down to verify that it satisfies the wiggle property. Starting from the first pair, nums 0 is 3, which is less than or equal to nums 1, which is 5. Then, nums 1 is 5, which is greater than or equal to nums 2, which is 1. Similarly, nums 2 is less than or equal to nums 3, nums 3 is greater than or equal to nums 4, and finally, nums 4 is less than or equal to nums 5. This pattern holds for the entire array, so the wiggle property is satisfied. It's important to note that there can be multiple valid outputs for this problem, and this is just one of them. Another example starts with an input array 1, 2, 3, 4, 5, 6. For the second example, the input array 1, 2, 3, 4, 5, 6 is reordered to 1, 6, 2, 5, 3, 4. Let's verify that this output satisfies the wiggle property. The first pair, nums 0, is 1, which is less than or equal to nums 1, which is 6. Then, nums 1 is greater than or equal to nums 2, which is 2. Similarly, nums 2 is less than or equal to nums 3, nums 3 is greater than or equal to nums 4, and finally, nums 4 is less than or equal to nums 5. This pattern holds throughout the array. Another example involves an input array 10, 3, 8, 2, 7, 4, which is reordered to 3, 10, 2, 8, 4, 7. Let's check how this satisfies the wiggle property as well. For the third example, the input array 10, 3, 8, 2, 7, 4 is transformed into 3, 10, 2, 8, 4, 7. Looking at the pairs, nums 0 is 3, which is less than or equal to nums 1, which is 10. Then, nums 1 is greater than or equal to nums 2, which is 2. Continuing, nums 2 is less than or equal to nums 3, nums 3 is greater than or equal to nums 4, and finally, nums 4 is less than or equal to nums 5. Again, the wiggle property is satisfied throughout the array. Now, let's consider some constraints and edge cases. The input array has a length n between 1 and 10,000, and each element can range from -10⁻9 to 10⁻9. The solution must work in place, without using extra memory, and it should run in O(n) time complexity. Let's explore some edge cases next. In terms of edge cases, there are a few scenarios to keep in mind. First, if the array contains only a single element, like 1, it already satisfies the wiggle property because there are no neighbors to compare. Similarly, if the array is already wiggle sorted, such as 1, 6, 2, 7, 3, 8, it doesn't need any changes. For arrays with just two elements, like 4, 2, we need to ensure the first element is less than or equal to the second, resulting in 2, 4. Finally, if the array contains duplicate values, like 2, 2, 2, 2, it already satisfies the wiggle property because all elements are equal, so no reordering is needed. These examples and constraints illustrate the flexibility of the problem and the importance of handling all edge cases correctly. To tackle the wiggle sort problem, one approach we can consider is using a brute force strategy. The intuition here is straightforward but computationally expensive. If we were to generate all possible permutations of the array, we could check each one to see if it meets the wiggle condition, that is, the elements alternate in their comparison, such as nums 0 equals nums 1 equals nums 2 equals nums 3, and so on. A slightly more practical brute force method involves sorting the array first, then rearranging it to satisfy the wiggle condition. Here's how this works. After sorting the array in ascending order, we swap adjacent elements starting from the first index, so indices 1, 3, 5, and so on. By rearranging in this way, we ensure the wiggle property is maintained. However, while this approach is somewhat simpler to implement, it comes with limitations. Sorting the array requires n log n time, and although the rearrangement is linear, the overall complexity remains n log n. Additionally, sorting changes the relative order of elements, which may not be necessary for certain inputs. This makes the brute force approach less efficient and often suboptimal compared to more direct methods. A more efficient solution to the wiggle sort problem is the one-pass greedy algorithm. The key insight here is that we don't need to sort or rearrange the entire array extensively. Instead, we can enforce the wiggle property dynamically as we traverse the array. The rule is simple. At even indices, the current element should be less than or equal to the next element, while at odd indices, the current element should be greater than or equal to the next element. If the condition is violated at any point, we simply swap the current element with the next one to restore the wiggle condition. To implement this, we iterate through the array from the first index to the second to last index. At even indices, if nums I is greater than nums I plus 1, we swap them. At odd indices, if nums I is less than nums I plus 1, we swap them. This ensures that the array satisfies the wiggle property at every step, and since we're only traversing the array once, the algorithm is highly efficient. When analyzing the optimized one-pass greedy algorithm, its efficiency becomes immediately clear. In terms of time complexity, it operates in n, as we only traverse the array a single time. For space complexity, it's 1, since all swaps are performed in place without requiring additional memory. This makes the algorithm not only fast but also very space efficient. Another advantage is its simplicity. It's easy to understand and implement, while also maintaining the relative order of elements whenever possible. However, there is a limitation to keep in mind. The algorithm assumes that modifying the input array in place is acceptable, which may not always align with certain use cases where the original input must remain unchanged. Despite this, the combination of efficiency and simplicity makes the greedy approach a standout solution for this problem. The one-pass greedy algorithm stands out as the optimal strategy for solving the wiggle sort problem. It achieves the desired result in n time, which is the best possible for this problem, and it uses no additional space, making it highly efficient. Another key advantage is its simplicity. It avoids unnecessary operations like sorting and focuses solely on enforcing the wiggle property dynamically during a single traversal. The core insight here is recognizing that there's no need to sort or fully rearrange the array. By handling violations of the wiggle condition locally, as we iterate, the greedy approach becomes both elegant and practical. Compared to the brute force method or sorting-based solutions, the greedy strategy minimizes computational overhead, making it far more scalable for large inputs. This is why the one-pass greedy algorithm is the clear choice for solving this problem effectively. A wiggle sequence is a special ordering of numbers where adjacent elements alternate between greater than or equal to and less than or equal to. For example, in the sequence 1, 6, 4, 8, 2, the relationships alternate as follows: 1 is less than or equal to 6, 6 is greater than or equal to 4, 4 is less than or equal to 8, and 8 is greater than or equal to 2. The goal is to rearrange the given array into this pattern efficiently. To begin, we can think about a brute force approach. The idea would be to generate all possible permutations of the array and validate each one to check if the wiggle condition is met. While this approach ensures we find a correct solution, it is computationally expensive, and we will explore its steps and limitations in detail. First, we sort the input array. Sorting helps in generating permutations systematically, as the elements are now in lexicographical order. For instance, if the input is 3, 5, 2, sorting results in 2, 3, 5. After sorting, we use a backtracking algorithm to generate all permutations of this array. This process systematically explores all possible orderings, such as 2, 3, 5, 2, 5, 3, 3, 2, 5, and so on. For each permutation, we then validate whether it satisfies the wiggle condition. For example, if we check 2, 5, 3, we confirm that 2 is less than or equal to 5, and 5 is greater than or equal to 3. Once we find a valid permutation, we stop early and return it. This approach ensures correctness but involves high computational overhead, as generating permutations and validating each one can be time-consuming. When analyzing the complexity of this brute force approach, we see that generating all permutations requires O(n) time, where n is the size of the array. Additionally, validating each permutation takes O(n) time, resulting in an overall complexity of O(n). *n. In terms of space, storing all permutations also requires O(n) space. These factors make the brute force approach impractical for larger arrays, as the factorial growth quickly becomes unmanageable. However, it is feasible for small input sizes, such as arrays with 6 elements or fewer. Sorting the array initially has a complexity of O(n) log n, and while it helps organize the permutations, it does not reduce the overall factorial complexity. Simple data structures like arrays and a backtracking stack are used in this approach. Key operations, such as generating permutations and validating the wiggle condition, are conceptually straightforward but computationally expensive. To optimize beyond the brute force approach, we can explore alternatives like a greedy algorithm. Instead of generating all permutations, a greedy strategy directly rearranges the array into a wiggle sequence in linear time, O(n). One effective method involves swapping adjacent elements to enforce the wiggle condition. This eliminates the need for permutations, drastically improving efficiency. Additionally, we must account for edge cases. For instance, an empty array requires no processing and can be returned as is, while a single element array trivially satisfies the wiggle condition. If the input array already meets the wiggle condition, we can return it without modification. Arrays with duplicate values require careful handling, as multiple valid wiggle sequences may exist. Taking the example of 3, 5, 2, sorting gives 2, 3, 5. From the permutations, we validate each sequence and find that 2, 5, 3 satisfies the wiggle condition. This output demonstrates the process but highlights the inefficiency of brute force, reinforcing the need for optimized approaches. The provided solution implements a direct and efficient approach to solve the wiggle sort problem. Here is the step-by-step explanation. 1. Class definition and method. The solution is encapsulated in the solution class, and the main method WiggleSort modifies the input list nums in place to achieve the desired pattern. 2. Iterating through the array, a single loop runs from index 0 to len, nums, 2. For each index I, we check whether the current element at nums, I, satisfies the wiggle property with respect to the next element nums, I plus 1. 3. Wiggle condition check. If the index I is even, the condition nums, I, equals nums, I plus 1, must hold. If it doesn't, the elements at nums, I, and nums, I plus 1, are swapped. If the index I is odd, the condition nums, I, equals nums, I plus 1, must hold. If it doesn't, the same swapping logic is applied. For swapping elements, when a violation of the wiggle condition is detected, the two adjacent elements are swapped to restore the wiggle property. 5. In-place modification. The array is modified directly without using additional space, making the solution memory efficient. ### complexity analysis. Time complexity. The loop runs in O(n), where n is the length of the array, as each element is processed once. The comparisons and swaps are constant time operations. Space complexity. The algorithm uses O(1) additional space since it operates directly on the input array. ### edge cases. The code handles various edge cases effectively. If the input array is empty or contains only one element, the loop does not execute, and the array remains unchanged. Arrays with all elements equal are already in wiggle order and require no changes. This implementation is both elegant and optimal, adhering to the constraints and requirements of the problem statement. This is the Java implementation of the wiggle sort problem, LeetCode number 280, with the same logic as the provided Python solution. The method iterates through the array and swaps adjacent elements to ensure the wiggle sort property is maintained. Key differences between Java and Python include type declarations for variables and the use of explicit array indexing. The code is concise and adheres to Java conventions, encapsulating the functionality within a class structure. To begin the solution walkthrough, we have the input array nums equals 3, 5, 2, 1, 6, 4, which contains 6 elements. The wiggle sort algorithm processes this array step by step to ensure the required pattern. Starting with iteration 0 at index 0, since the index is even, we check if the current element is greater than the next element. Here, nums 0 equals 3 is less than nums 1 equals 5, so the condition is false and no swap is needed. The array remains 3, 5, 2, 1, 6, 4. Moving to iteration 1 at index 1, the index is odd, so we check if the current element is less than the next. Here, nums 1 equals 5 is greater than nums 2 equals 2, which satisfies the condition. Therefore, we swap these two elements, resulting in nums equals 3, 2, 5, 1, 6, 4. Next, in iteration 2 at index 2, since the index is even, we examine whether the current element is greater than the next. Here, nums 2 equals 5 is indeed greater than nums 3 equals 1, so the condition is true, and we swap these elements. This updates the array to nums equals 3, 2, 1, 5, 6, 4. In iteration 3 at index 3, with an odd index, we check if the current element is less than the next. Here, nums 3 equals 5 is less than nums 4 equals 6, so the condition is false, and no swap is needed. The array remains 3, 2, 1, 5, 6, 4. Finally, in iteration 4 at index 4, the index is even again, so we check if the current element is greater than the next. Here, nums 4 equals 6 is greater than nums 5 equals 4, which satisfies the condition. We swap these elements, resulting in the final output nums equals 3, 2, 1, 5, 4, 6, for this example. In the second example, the input array is nums equals 1, 6, 3, 4, 2, 5. Once again, the algorithm processes the elements step by step. Starting with iteration 0 at index 0, the index is even, so we check if the current element is greater than the next. Here, nums 0 equals 1 is less than nums 1 equals 6, so the condition is false, and no swap is needed. The array remains 1, 6, 3, 4, 2, 5. In iteration 1 at index 1, the index is odd, so we check if the current element is less than the next. Here, nums 1 equals 6 is greater than nums 2 equals 3, which satisfies the condition. We swap these two elements, updating the array to nums equals 1, 3, 6, 4, 2, 5. Continuing with iteration 2 at index 2, since the index is even, we check if the current element is greater than the next. Here, nums 2 equals 6 is greater than nums 3 equals 4, so the condition is true, and we swap them. This updates the array to nums equals 1, 3, 4, 6, 2, 5. For iteration 3 at index 3, the index is odd, so we check if the current element is less than the next. Here, nums 3 equals 6 is greater than nums 4 equals 2, which satisfies the condition. We swap these two elements, resulting in nums equals 1, 3, 4, 2, 6, 5. In iteration 4 at index 4, with an even index, we check if the current element is greater than the next. Here, nums 4 equals 6 is greater than nums 5 equals 5, which satisfies the condition. After swapping these elements, the final output for this example is nums equals 1, 3, 4, 2, 5, 6. In the final example, the input array is nums equals 4, 1, 7, 3, which contains 4 elements. Starting at iteration 0 with index 0, the index is even, so we check if the current element is greater than the next. Here, nums 0 equals 4 is greater than nums 1 equals 1, which satisfies the condition. We swap these elements, resulting in nums equals 1, 4, 7, 3. In iteration 1 at index 1, the index is odd, so we check if the current element is less than the next. Here, nums 1 equals 4 is less than nums 2 equals 7, so the condition is false, and no swap is needed. The array remains 1, 4, 7, 3. Finally, in iteration 2 at index 2, since the index is even, we check if the current element is greater than the next. Here, nums 2 equals 7 is greater than nums 3 equals 3, so the condition is true, and we swap these elements. This results in the final output array nums equals 1, 4, 3, 7. With this, the wiggle sort is complete for this example, as the array now satisfies the required pattern of alternating peaks and valleys. The time complexity of the wiggle sort solution is O(n), where n represents the length of the input list, nums. This is because the algorithm operates using a single for loop that iterates from the start of the list to the second to last element. Specifically, the loop runs for n1 iterations. Within each iteration, the algorithm performs a constant time operation. First, there is a conditional check that evaluates whether the current element and its neighbor satisfy the wiggle property. This involves simple arithmetic and comparison operations, which are O(1). If the condition is not met, a swap operation is performed to rearrange the two elements. In Python, swapping two values is also an O(1) operation. Since each iteration takes constant time and there are n1 iterations, the overall time complexity becomes O(n1 ** O(1), which simplifies to O(n). Importantly, this time complexity holds consistently across the best, average, and worst cases, as the algorithm always performs exactly n1 iterations, regardless of the input's order. While the number of swaps may vary depending on the arrangement of elements, this variation does not influence the overall time complexity since each swap is O(1). The space complexity of the solution is O(1), because the algorithm is designed to work in place without utilizing extra memory for additional data structures. Instead of creating a copy of the input array, the algorithm modifies the given list, nums, directly. The memory usage is limited to the loop variable, I, which is a simple integer that requires constant space. No auxiliary data structures, such as lists, dictionaries, or recursion stacks, are used, and all operations are performed directly on the input list. As a result, the space requirement does not grow with the size of the input, making the total space complexity O(1). This in-place approach is a key factor in the algorithm's efficiency, as it minimizes the use of additional resources while achieving the desired wiggle property. When comparing the provided solution to a naive or brute force approach, the advantages become clear. A naive approach might involve sorting the input array first to rearrange elements into the wiggle property. Sorting alone takes O(n log n) time, and the subsequent rearrangement would add another O(n) time, resulting in a total time complexity of O(n log n). In contrast, the provided solution bypasses the need for sorting entirely. By checking and swapping elements in a single pass, it ensures the wiggle property in O(n) time. This direct approach is more efficient because it minimizes unnecessary operations. Both the naive and provided solutions share the same space complexity, O(1), as neither requires additional data structures. However, the provided solution is optimal because it achieves the desired result with fewer steps and avoids the overhead of sorting the input array. To mathematically confirm the time and space complexity, let's break it down further. For time complexity, consider that the algorithm uses a single for loop that iterates n1 times, where n is the length of the input array. Within each iteration, the operations, including the conditional check and potential swap, are constant time, or O(1). Multiplying the number of iterations by the time taken per iteration, we get n1 * O(1), which simplifies to O(n). For space complexity, the algorithm does not allocate memory for additional data structures. The only extra space used is for the loop variable, I, which is a single integer and requires constant memory. Therefore, the space complexity is O(1). Together, these calculations confirm that the algorithm achieves O(n) time and O(1) space complexity, making it an optimal solution to the wiggle sort problem. When working on wiggle sort problems, there are several common mistakes to be aware of. First, misunderstanding the wiggle condition is a frequent issue. Some assume the condition must strictly alternate as less than, greater than, or vice versa, but the sequence can start with either less than or equal to or greater than or equal to. This flexibility is often overlooked and can lead to incorrect solutions. Another mistake is sorting the array as a first step, which might seem logical but fails in many non-trivial cases because a wiggle sequence depends on the relative order of elements, not a strictly sorted order. Additionally, overcomplicating the solution by generating all permutations or using nested loops can lead to inefficient algorithms with factorial or quadratic time complexity, which are unnecessary when linear or greedy approaches are available. It's also important to handle edge cases carefully, like arrays with very small sizes or those with all elements equal. Finally, if the problem requires in-place transformations, creating a new array instead of modifying the original one can result in wasted space or even cause you to fail memory constraints. Recognizing these pitfalls can save you time and help you craft more robust solutions. Now, let's talk about insights that are particularly useful in interviews. Wiggle-related problems often revolve around pattern recognition, where you alternate between conditions like peaks and valleys. A greedy approach is usually the best way to think about these problems, focusing on local adjustments instead of aiming for a global solution upfront. Interviewers also expect you to identify optimal time complexities. Most wiggle problems can be solved in O(n) or O(n log n) time, and it's important to justify why your solution is efficient. If you start with a suboptimal solution, make sure to clearly communicate its trade-offs and explain how your final solution addresses those limitations. Testing edge cases is also crucial, so remember to validate your solution with inputs like arrays containing repeated values, very small sizes, or those that are already in a wiggle-sorted state. For additional practice, related problems like LeetCode 376, which focuses on finding the longest wiggle subsequence, or LeetCode 324, a more advanced wiggle sort problem, can help you deepen your understanding. Problems like LeetCode 31, which deals with permutations, or LeetCode 406, which involves relative ordering in greedy contexts, are also highly relevant and worth exploring. Finally, let's explore some alternative approaches and their trade-offs. A brute force method involves generating all possible permutations of the array and validating each one for the wiggle condition. While simple in concept, this approach has a factorial time complexity, making it highly inefficient for larger inputs. A much better alternative is the greedy approach, where you traverse the array and adjust neighboring elements to ensure alternating peaks and valleys. This method is both efficient, with O(n) time complexity, and straightforward to implement. Another option is a sorting-based approach, where the array is sorted first, and elements are alternated between smaller and larger groups. While this can work effectively, it requires O(n log n) time and may not meet in-place requirements if those are specified. Lastly, dynamic programming can be applied by tracking increasing and decreasing subsequences, which is particularly useful for maximizing subsequences. However, for simpler wiggle problems, dynamic programming is often more complex than necessary. Understanding these trade-offs can help you select the most appropriate solution for the problem at hand. Great job! To wrap things up, we reviewed the core concepts of wiggle sort, discussed its complexities, and highlighted key takeaways. Keep practicing these types of problems to strengthen your algorithmic thinking. Thank you for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!